Mina was one of my PhD students for the last 1.5 years of her PhD. Originally, she worked with Torbjörn Dahl and Angelo Cangelosi and several externals. That was one of the most extraordinary PhDs. I never had to supervise a PhD with 5 or maybe even 6 supervisors, so that was quite a bit. And it's since it was Torbjörn and Angelo, it was of course in the field of robotics, but even more interesting, it was in emotional robotics, and that was the topic of her PhD. She has handed in, she has defended. There are some minor changes to do, which, to my knowledge, haven't been handed in yet, but there's a little bit more time. And we nonetheless thought that it would make good sense if she presents her results in this community. And that's more or less all I have to say. Mina moved to the company that makes these robots, as far as I'm aware. The head you see in the back of her
Yes.
picture, and so she got a job already and is doing research in that company. Mina, do you want to go?
Yes, thank you. Thank you so much for the invitation.
Hello?
It's a great opportunity for me to have this chance to talk about this work, which basically half of this work was done in Plymouth University. And then I continued the second part at SoftBank Robotics. I'm not anymore affiliated with SoftBank Robotics now. And so let me see, I'll try to share my screen now. Yes. Okay. Sorry for that. Yep. Can you see my screen?
Yes.
Okay, perfect. So I will
Yes.
talk about emotional body language synthesis for humanoid robots. And I will start a little bit about emotion in humans, some very basic stuff. Emotion can actually be analyzed in as 2 different functions in humans. The first one is the internal aspect of emotion, which is basically used for the organization of our behavior. Like it guides our action selection or our attention, motivation, etc. And then we have the external aspect, which is actually emotion as a signal for communication and social coordination. And both of these aspects have been co-evolved in humans, and they are important for survival and performance. All emotions comprise of behavioral, cognitive, and neurophysiological components. And to put the things I'm going to talk about in perspective, we are basically interested in the external aspect, that is emotion in terms of communication, and the behavioral component of emotion. Now I have this prompt here, which basically these are paintings, images of paintings from Wiki Commons. And I thought it might be easier to perceive how the non-verbal expression of emotion, it can be described either from facial expression or from body language. And here we see from these paintings that depict states of emotion that both these signals, face and body, are very important. And people pay attention to body as much as face, although facial expression studies have been dominant for years. Emotional body language is equally important, as we can see from the paintings. We get this information readily, like in a subconscious way or conscious way as well. And the emotional body language, or EBL for short, is important because body movement is perhaps the most primitive way to convey affect. It can be perceived from distance. It's less susceptible to social editing, so we can mask our facial expression much easier than we do with our body language. And it's more effective in communicating intense positive or negative emotions. It's indicative of the overall likability, the interest and openness between individuals, for example, in a conversation, and it draws attention. Now let's move to human-robot interaction. And here, emotional communication is essential, especially for socially interactive robots. And when I say socially, we can think of robots deployed in social environments such as schools, hospitals, care homes, shops, etc. And it's important in terms of social presence. It can be used to render a robot as a believable character, which is important for having an engaging interaction. And also, emotion can be employed as a means to provide feedback about a robot's internal state, goals, intentions, etc. For instance, a robot that detects some risky behavior, it can employ an expression of fear to alarm people around it. The reason we think emotional body language is also very important in human-robot interaction is that many robots have static faces, like this one, and so body language is a nice alternative way to express emotion. Also from studies, we know that individuals are more likely to interact with robots that move, and also emotional personality makes interaction more enjoyable. And to these arguments, we can also add what we said before about visibility from distance, or the trustworthiness of the body language, because it cannot be masked easily, and so forth. Now I will talk a little bit about prior approaches and challenges in designing emotional body language for humanoid robots. The first approach is direct human imitation. And here computer vision techniques, markers and sensors are used to track key joints from human emotional body language. And then these values are mapped to the robot joint space. The results are human-centric style of motion. The advantage is that this is an end-to-end process, but the problem is that finding a good transfer function can be quite challenging due to morphological differences between humans and robots. The second approach is feature handcrafting. Here, human EBL is observed, analyzed, annotated, and features are extracted. Features such as body orientation, symmetry, force, velocity, and so forth. Again, we have, as a result, a human-centric style of motion. These features are very well validated, but the problem here is that the method is hand-coded, and that can be cumbersome. Finally, pose-to-pose animation, which is inspired by graphic design animation. Here, the animator works in a with a creative approach. The animator conceives some expressive postures, and then having the robot morphology in mind. And then these postures are interpolated to produce a sequence, an animation. The difference from the previous approaches is that this method produces a robot-centric style of motion with increased lifelikeness, since it's adapted directly to the robot's morphology. But the problem again is that the method is hand-coded. And so we discerned two main challenges, limitations with the previous approaches. The first one is hand coding, which can be cumbersome. So it results in a limited number of expressions and also in limited granularity. And this makes the behavior of the robot repetitive and predictable after a while, which cannot be engaging, especially in long-term interaction. The second problem is that the human-centric style of motion used by some of these approaches might not be lifelike enough for the much simpler morphology of a humanoid robot. And so our proposed approach is based on robot-centric style of motion, and we use as a training set for our algorithm. We used a small set of pose-to-pose designed animations. So according to the third approach I presented before. And then we also use a data-driven end-to-end alternative by employing generative models, and more specifically, the variational autoencoder framework. The objective is to learn essential features and be able to generate numerous new animations that will appear realistic and lifelike. And here I would like to make a note that there is some work that was done in parallel with ours, but completely independently. You can see here the reference. In this work, they used cycle guns, but they were focused on a human-centric style of motion. And so you can check this work as well too, if you are interested in deep learning approaches for emotional body language generation. Now, the first thing someone has to decide when working on affect generation is the emotional representation. And there is a huge debate for ages on this subject, with the categorical representation being the one used more extensively. So the categorical representation is basically the 6 basic emotions like happy, sad, angry, fearful, etc. And you use these classes to cluster different affect states. The second approach is the dimensional representation, and this is the one we adopted for our work. And most specifically, the circumplex model, which uses 2 dimensions, valence and arousal. And we can see here in the schematic, so we have the x-axis where valence is, ranging from unpleasant to pleasant, and then on the y-axis, arousal ranging from deactivation to activation. And we have, for instance, anger here as a data point in this 2D space that has a very low valence and a very high arousal. So we can depict every emotional state like that. And the advantage here is that this is a continuous numerical representation that can be highly discretized. So we don't really aggregate many different states of emotion in just a few categories, but instead we can have a unique descriptor for each state. And that allows us to capture very subtle differences between different states. For us, yeah, I will talk a little bit for the animation set, and I will continue on that later. So the animation set we used was created with the post-to-pose method, and basically we had 36 animations created for a Pepper robot, which we selected from a broader animation library from SoftBank Robotics. And the objective was to have 4 animations in each class of a dimensional effect. So we have these 9 classes here. Valence was split in 3 levels: negative, neutral, and positive. And then arousal in 3 levels: tired, calm, and excited. So we tried to get 4 animations in each of these classes as a pre-selection. And now, from a technical perspective, an animation is basically a sequence of postures. And we can see a posture here of the Pepper robot. And each posture is described with 17 values, one for each of the 17 joints of the robot. And some of these animations had also some additional modalities like ILEDs, colors, or vocal nonverbal sounds. And here is our experimental procedure in the first phase, where we wanted to label these animations with valence and arousal scores. So we had 20 participants, and the trials were the setup of the experiment. You can see it in this picture. That was in Plymouth University, and the interface for the user is the one here, where the user clicks at the play button. The robot executes one of the 36 animations in a randomized order, and then the participant would rate arousal and valence on these sliders. Here we call valence as pleasure to make it more intuitive for the participants. And the numbers here are hidden from the participants, but the range here is from 0 to 1, highly discretized. And after they submit the ratings for each animation, there are two Likert scales asking them how confident they felt in their judgment for arousal and for valence. So here are the results from this first experiment. We actually conducted a reliability analysis, and we had a very high consistency among the raters, the participants. So we aggregated all these results by averaging across participants for each animation. And here you can see these ratings projected on the 2D affect space with valence and arousal. And each data point is the rating for each animation. And the tags you can see here were actually not used at all during our first experiment. These tags were assigned from the animators when they initially created each animation, but I have put them here so that we can contrast our results with the initial subjective opinion of an animator when they created the expressions. And but you can see in some cases, like in many cases, actually there is an agreement, like happy is high valence and high arousal here, or excited and joyful, etc. One thing we notice here is that this lower space is not covered by ratings, so participants didn't feel that some of the animations had a place here, like where high valence is and low arousal. And but in total we had 36 animations reliably labeled with valence and arousal scores. In the next step, I will talk about the generative process. Initially we used a standard variational autoencoder. I will explain a little bit about that. I will use this picture, which is a picture of a standard autoencoder. So what an autoencoder does is it takes an input X and basically it learns to reconstruct it. And in doing so, it compresses its input X into a lower dimensional representation. We call it latency representation. And then this latency representation passes through the decoder part and decompresses into X. And there is a reconstruction error used, measuring the distance between reconstruction and original to penalize the model accordingly. Here, in the standard autoencoder, this layer is a deterministic layer. So basically, vector Z is a deterministic vector. But the variational flavor of this model allows this layer here to be stochastic and basically to represent a distribution, which we call latent distribution. And here the loss function accordingly, besides the reconstruction error, has also this regularization term, which makes sure that this latent distribution will be constrained similarly to a well-known and nicely behaving distribution like the normal distribution that will allow make the training more easy and will allow us to sample it later on and generate new expressions. So basically this difference here is what makes the variational autoencoder a generative model, because instead of having just deterministic Z representation, instead we have a whole distribution which we can sample and generate many more samples, new samples. And here we can see our architecture with the architecture we used for the emotional body language variational autoencoder. We feed it with a posture, and this is the encoder part. The posture is compressed to a three-dimensional latent distribution, and then decompressed again to give the original posture. And after we have trained this model, we can remove the encoder part and we can sample this latent distribution and generate new samples, new animation and new postures. And more specifically, here we can see the latent space of the learned model in which we have encoded all our original animations. And so every data point here is basically a posture, and every color signifies a different animation. So you can see that when we have subsequent postures in an animation, they are encoded near each other in this latent space. And so after we finish with the training, we can remember we constrained our learning with a Gaussian distribution. So we can sample a three-dimensional Gaussian distribution to generate new postures. And we can also interpolate in the latent space these samples and get a trajectory of postures, which we can decode then into an animation in the 17-dimensional joint space. Okay, so in this phase of our work, we also wanted to explore this latent space a little bit further and to see what is the granularity potency, how what variation we can have between different animations generated from this latent space. And also we want to see if there are any topological features or geometrical features in this three-dimensional latent space that could be used to generate targeted emotion. Because so far we can only generate emotional animations since we trained with emotional animations, but we are not able to generate animations of specific emotion. And so to do that, we use this idea of spherical grids. And this is a spherical grid here projected in the latent space. And we use the longitude lines of these grids as latent trajectories to be decoded into animation. So each of these lines here are decoded later into different animations. And to make it as systemic as possible, this exploration, we also scaled the radius of these grids, as we can see here. So we have the blue one, which is near the center of the latent space, and then we extend the radius to go towards the outer latent space. So we had 10 different ranges, 10 different values for the radius. And we also had 3 rotations of these grids. So this one is parallel to the latent dimension 3, while these grids here are parallel to latent dimension 2. So in total with these manipulations, we generated 300 animations in the 17th dimensional joint space of the robot. And here, after we decoded these animations, these 300 animations, we collapsed their 17 dimensions into one by averaging them to be able to inspect the differences better. So every line you see here, this graph is basically one animation. And we have 10 different blocks, as you can see here, one for each longitude line of the spherical grid. And then we also have these 3 rotations of the grid, the 3 panels here. And the colors indicate the different radiuses from 0.5 to 10. And you can see here that the black lines are radius 0.5. And you can see that when we sample something from the center of the latent space, there is no it's pretty smooth and there's not much variation. But as we go outwards, like the white lines are a radius of 10, then we see that the amplitude of the expression is heightened, and also there is more variability. So from this exploration, we're able to deduce that there is an inherent possibility for granularity in the latent space. As you see, all 300 decoded animations are different from each other. And then also, we thought that maybe we can use the radius as a modulator for the arousal content of the generated animations, because arousal is actually how activated or deactivated the robot is during an emotional expression, and probably amplitude and variation could be a good proxy for that. So this we will test in the next we tested in the next experiment I will present, but let me show you the same results here. I will just show the radius effect. So here we see the robot in the simulator, and the radius is 0.5. So there is just minimum, even not almost not perceived motion. And then we increase to 3 and to 6, and the motion is increasing, and also the variability is increasing. And at some point, if you increase too much, then you exceed the limits of the learned latent space, which is basically like a sphere, and you get some unnatural postures. But it's not hard to find where the limit is. In our case, it was around 7. Okay, so in the third experiment, we had this candidate feature for arousal, but we also need something to condition valence. And this, we didn't find a solution from the exploration we did before. So we adopted this conditional variation autoencoder model, where besides your input, you also add this condition to the encoding phase, and then again to the decoding phase. And in our case, this condition was the valence label we collected from our first experiment, which is a scalar. And we also added some more, one more modality as an input. So besides the motion, the 17 joints, we also added 48 values for the ILEDs of the robot. And so we concatenated this input along with the valence score. And so we trained this network, and we were able to generate many animations. And then we designed this evaluation study. For this study, we had to make it a bit more systematic in terms of valence and arousal conditioning. And for valence, we had 3 levels. We had, for these 3 levels, we conditioned the CVA, the conditional variational autoencoder, with 3 different values. With 0 to generate negative valence animations, 0.5 for neutral animations, and 1 for positive animations. So the generative process was conditioned with these 3 different values. And for arousal, we used 3 levels of arousal, low, medium, and high, obtained by sampling the 3-dimensional latent space with a radius of 3, 4, and 5, respectively. So in total, we had 3 by 3 levels, 9 combinations, and we had 2 samples, 2 animations for each level. In total, we had 18 generated animations to evaluate. The experimental design was as follows. The first part, we actually displayed a set of designed animations. So like similar to our original animations we used for the training, that was animations created with a post-pose method from professional animators, and we contrasted them with generated animations from the CVA network. And we asked people to rate both without knowing which one is which, of course, randomized, in terms of anthropomorphism and animacy. These are 2 scales from the Godspeed questionnaire. In the second part, part B, we did the main evaluation of the generated animations, the 18 generated animations, in terms of valence and arousal. And in the third part, we just repeated part A to have a pre-test and post-test result. And we had 20 participants for this experiment. Here we can see the interface. It's similar to the one we used for our first experiment. We have sliders. Displays placed is for valence, inactive, active is for arousal. And we added one more pilot dimension, which is dominance, which ranges from submissive to dominant. And after each trial, we also asked 2 questions. The first one was, the robot's behavior draws my attention. And the second one, the robot's expression was emotional. This one was more like a manipulation check. And we had 3 hypotheses. The first hypothesis is that valence ratings from the participants for animations generated with negative valence conditioning will be lower than those for animations generated with neutral or positive. And also that the valence ratings for animations generated with neutral valence conditioning will be lower than those of animations generated with positive. And for arousal, our hypothesis is that the ratings will be, for animations generated with low arousal, will be lower than those of animations generated with medium or high. And ratings for animations generated with medium arousal will be lower than those of animations generated with high. And the third hypothesis was that participants will not perceive any significant difference between designed and generated animations. So here is the result for hypothesis 1 and 2. And let's see on the left first, which is for valence conditioning. We had 3 levels of valence conditioning, negative, neutral, and positive. And we can see here that the trend is according to our hypothesis. So negative conditioning had lower ratings than neutral, and neutral lower than positive. However, the statistical analysis showed that only the difference between negative and neutral and negative and positive was significant. So neutral positive was not significant. For arousal, again, we have low, medium, and high conditioning for our CVAE generated animations. And we see again that the trend is according to our hypothesis. But again, although we're able to find statistically significant results for low versus high and medium versus high, we're not able to have a significant result for low versus medium. And the next result is for the anthropomorphism and animacy between generated and designed. We were not able to find any significant differences here. So our third hypothesis is actually confirmed that there are no perceived differences. And we can see here for anthropomorphism, these are the Likert scale scores, like from 1 very low anthropomorphism to 5. And the different colors here are the designed and generated sets, pre-test and post-test. In all cases, there were no significant differences. And here is the two last questions results. So for the robot, the question was the robot behavior draws my attention. And here we found that the red line for attention valence conditioning. So the negative valence, the red line here, was significantly higher in drawing people's attention than neutral. And you can see that also positive conditioning is pretty high. It's just that we didn't find any significant difference between positive and neutral, but we found for negative versus neutral. And also for arousal conditioning, we saw that animations with high arousal, generated with high arousal, draw people's attention significantly more than low and medium arousal. And finally, for the question, the robot's expression is emotional, we found that for the valence conditioning, that negative, the blue line, negative and positive animations were considered as more as emotional compared to neutral. And then for arousal, we found that animations of high arousal were considered as more emotional. Okay, so the conclusions here, we partially justified our two hypotheses. And again, the problem with the part we were not able to justify, although we saw that existed as a trend, was this poor discrimination, again, in the same lower right corner of the two-dimensional affect space, as we saw in the first graph of the labels. And this is the space where we have high valence and low arousal. So we are not sure if the problem is that because of the data set, since our original set that we used for the training had this problem from the beginning, but also I have come across to a couple of other studies that they mentioned that they also had a problem to create animations that would be assigned to this space of high arousal and low arousal and high valence. This needs to be examined a bit further. And we had our third hypothesis confirmed, so there are no significant differences between how people perceive the designed and the generated animations in terms of anthropomorphism and animacy. And also we found that negative valence, animations with negative valence draw more attention compared to neutral, which is a bit intuitive. And high arousal draws more attention compared to low or medium. And so maybe if we want to capture people's attention, we can use negative valence and high arousal. And then we also found that negative or positive valence is interpreted as more as an emotional, which is this manipulation check that confirms that what we generated is actually an emotion. And also high arousal is also interpreted more as an emotional reaction. Now, some future directions would be to integrate this emotion body language generative model with a recognition system, emotion recognition system, that can read the human's emotion or sentiment or situation, context, etc. And also another direction would be to try if we can use transfer learning of this model to a now robot, which has morphological similarities. And in terms of applications, one interesting application we can think of would be a robot-assistive therapy. So maybe we could use these emotional body language expressions as in interventions for children with ASD, for example. And here I have some links. We have actually released recently our data set with these animations, both the original ones and also the 18 animations we used in our evaluation. And they're in a form that can be used very easily for machine learning, deep learning models. And that would be interesting to see how other algorithms may be compared. And we also have some videos here in YouTube from each stage of our work. And here are my supervisors, collaborators, and people that advised me and helped me in this work. Yes, and if you have any questions, I would be glad to answer. I hope I didn't go through everything too fast.
No, thank you very much, Mina, for your presentation. Thank you.
You're welcome.
From the participants, is there any particular question? You can also use or type the question on the chat in case you may need, and I can moderate for you. Any questions?
Yes. That pepper robot is not particularly expressive. Yeah, it makes some cute noises and has these blinking eyes. Is that a severe constraint? If you would have had a robot that is more emotionally expressive, do you think the results would have been different in any way?
Yes, definitely in affect design, the platform is of a crucial role. And well, I would say like, yes, we can think of maybe androids as super expressive sometimes. Pepper is somewhere in the middle. It's not of actually 17 joints that can move. It's quite a good number of degrees of freedom to get some kind of expressive motion, but definitely yes, the more degrees of freedom, the better. The better results you can have in terms of expressiveness. And then yes, also other modalities are crucial. Like we didn't test that in our two experiments, but By seeing the animations we've got, and actually in this video, we have the VAE animations where the ILDs modality was not included. And when you compare with the CVAE, where we all studied this modality, you can perceive a difference. When you combine more than one modalities, you definitely get something more expressive. And also an idea would be for future work, maybe to also work with the non-linguistic sounds, since SoftBank Robotics has a huge library of such sounds for the robot. And we didn't work on that because we would need a separate model to work with audio. But yes, the more modalities you add, the better. And this is, I think it's called also in psychology, they call it like redundant signal. But in terms of affect expression, it's good to have a redundant signals. The better is, the more is better.
Thanks.
Oops, sorry.
Thank you very much. Any other questions from the participants?
Yeah, I've just got one. It was a really good presentation. Thank you.
Thank you.
My question is was the emotional state of the participants taken into account? You know, for example, if one of the participants having a bit of a bad day, would that have an effect on the results?
Yes, that's a very good question. Actually, we did that in the first experiment. We used the PANAS questionnaire, which is a mood questionnaire, and you can rate the positive and negative mood of each participant. And the results were in a range that was considered acceptable according to the authors of the questionnaire. Was not like extreme negative or extreme positive. But truth is, we didn't repeat that for our second experiment, which we should have, but we felt that the workload was a bit more increased due to the fact that we had one more slider and a bit more difficult questions in the end. So yes, I think we should have done it again, although I would expect similar results as the first one. But yes, it should have been included. Because this is an important aspect, definitely. There are studies that show that where we are in a bad mood, we perceive things as more negative, and so on.
Yeah, thank you very much.
Thank you. Any other questions?
Yes, yes, of course. Yeah. Let me see what.
Go ahead, Thomas.
How close are we to truly emotional robots that really convince us and make us cry and laugh?
Oh, may I say that at some point, looking at a paper, maybe I was moved by the fact that this was our work, but it felt a little bit touching. And we also have one more video, although I was not able to upload it yet, where we actually use these expressions, and we had the paper to narrate a story for kids. I think that the girl with the matches, which was a sad story. And and we had this girl that we used as an actor, that she played the kid in this scenario where we had this video. And at the end, when we finished recording, she came up and her eyes were a bit like almost breaking out in tears, almost. And she said, "Oh, that was really touching, you know." So, but of course, it makes a difference here in terms of whether you are accustomed to the robot And whether you are a novel user of the robot,
Yeah.
definitely you can have different degrees of feeling touched by that. But so expression as a communication channel is one thing, but I think the most powerful scenario would be to connect it with some kind of functionality, as we said before, like a signal for danger, fear as a signal of danger, and maybe this would add a more substantial use for emotion expression. But yeah, in general, I don't know. I'm not sure how close we are.
Well,
I
but
think
you just said some people are crying already.
yes, but
So
yes,
it's
this is
more
in a very
complicated.
limited lab set, of course.
The question is definitely quite complex and depends on the answer depends on many things. Yeah.
Definitely.
Yeah, so but to some degree, of course, we do have artificial systems, robotic systems, not necessarily in physics, but in computer animations that are extremely touching. That's what you pointed
Yes.
out, of course.
Okay.
Yeah. So we are in the middle of the process to make
Yes.
artificial systems as emotionally touching as humans are.
Yes, and this is an important subject actually from the ethics point of view. I tried to touch it a little bit in my thesis, but of course it's not my expertise. But one of the questions I found, which I think it was quite reasonable, is like when you have a robot with kids, and kids can be much easily taken
Yes.
by such kind of expressions. What do you do? Do you prefer to have a robot that acts mechanically? And then you have kids might use some insulting language with such machines, like we've heard some examples with Siri and Alexa, and kids talking to them like in a very commanding way, and because they're mechanic for them and they will not react to any insult. Or you prefer to have something that has some kind of emotional reaction, so that the kid becomes a bit more careful about the behavior. So, but it's a big question. It's not, there is no clear cut answer which way is better.
Yep. Thanks.
Thank you very much. Okay. I think that then, is there any other questions from the participants? Okay. Okay, if not, then I think that we can close the talk, the webinar here. Mina, thank you very much for your presentation. Thank you also for supporting these activities, and best wishes for your future career.